horizontal. We've got the amount of, sorry? Okay,
Well,
I'll carry on.
apologies, Bob. I forgot to turn the recording on. I've just turned it on now.
Okay. We've got the energy and the steam at the bottom. So the more you heat it up, the more the energy increases. So if you take water here at A temperature, incidentally, I use the old-fashioned imperial system because I completely hate, loathe and detest anything metric. So we start here at A temperature and we add by the fire or whatever means energy into the water. And at some point, it stops going up this curve and levels out. And this is where the latent heat comes in, and it changes from water into steam over this period of time here, or energy increase. And as you put more heat in it, the water dries out. So at this end here, you've got dry saturated steam. Now, what saturated means, it's in contact with the water that's being generated from. If you take it out of contact with the water that it's generated from and add more heat, you got this curve here and it becomes superheated. So it's got more energy. As you go through that, you can see there's a hell of a lot of energy you pump in that latent heat phase. So what we're talking about in injectors is working around about here, dry saturated steam. Now, I said velocity was a key factor, and here you have a pressure, pounds per square inch, and velocity, feet per second up here. And everybody knows that the velocity of air in air of sound is 1100 feet per second. So at naught pressure, you've got naught energy, naught velocity. If you look at a steaming kettle, it's no pressure in it, it just oodles out the spout, doesn't it? So at 50 pounds per square inch, you've got practically twice the speed of sound. So there's a lot of velocity there. And if I double it to 100, you can see what's happening. So by the time you get to 250 pounds per square inch, you've got about 4 times the speed of sound. Anyway, bear that in mind as we go through the talk. Conversely, we have a water situation. If you measure the velocity of water against pressure, you get a curve something like this. So at 50 pounds per square inch, you've got about 80 feet per second, or nearly 60 miles an hour, or 60 miles an hour at 50. And it goes up, eventually it tails off. But this is the sort of area we're looking at for injectors. To understand an injector, we really need to know how ejectors work, because the first stage of an injector is in fact an ejector. So what do ejectors do? They create a partial vacuum. They work by friction of steam on air. They're used in boiler feed injectors, water lifters, for powering vacuum brake systems, and many other things, of course. The essence of the Stephensonian steam locomotive, the blast up the chimney, is all to do with ejectors. If you want to make them, there's simple rules to follow, which I've perfected, I think, and easy to make and quite efficient. So how do they work? Well, the key thing is this velocity. And the steam comes in here, if you can imagine that having come from a boiler down here, and hits this choke here and expands in the nozzle. And you hope it comes out as a parallel jet at this end. So if we look up here, what's happening as we go through the nozzle, the pressure is decreasing till at the outlet, it's either at or just below atmospheric pressure. And conversely, it converts the velocity from fairly low at this end to quite high at this end. And that's what we're looking for, a high velocity in here, which you'll see in a few minutes the reason why. So an air ejector consists of a converging diverging nozzle discharging into another converging diverging nozzle. steam in through here, that entrains the air and forces it out at the other end. This is the vacuum brake gear, ejector and valve I made for my 5-inch gauge roe deer, B1. And that's an intriguing bit of kit that I made. I don't know how I managed it, but it did work very well. Now then, Monsieur Henri Giffard. He was a French military engineer who was tasked with making a hot air balloon, and he wanted it powered. Well, the only power you had in those days was really steam. Well, to have pumps on board a dirigible balloon weighing a lot of kilograms to him just wasn't on. So he was experimenting with nozzles, and he came up with the Injector. This isn't his original patent one. It's one that Davis and Metcalfe made, and it was supplied by Sharp Stewart. And I want you to look at all this gubbins up here. Now, when we come to some of the examples further on in the talk, you'll see just how clever this guy was to realize how you had to deal with the steam going through this nozzle to start the thing up. They were always a bit finicky to start up with, and I think it put off a lot of railway crews from their original use because they were difficult to start. And the last thing you want on a locomotive is difficulty in starting an injector. You want to open the steam, open the water, and away you go. So, standard life, I say standard, but this is more like the model ones, but the live steam ones are much the same, exactly the same principle, in fact. So here's our convergent divergent nozzle, and we call that the steam cone. And here's the air cone from the ejector, which we will now replace with a convergent cone. And that is called the combining cone. And at the other end is the delivery cone, which is a diverging nozzle. So that is the basics of your injector. So steam comes in there, cold water feed comes in here. There's a water and steam mixture. The steam condenses into cold water and comes out the other end of the combining nozzle here, jumps this gap, goes into the delivery cone, and comes out at high pressure at this end. Pressure energy, let's look at that. Force is pressure times area. Very simple. So pressure times area 1 there equals pressure times area 2 here. If I increase the pressure in here, this slider piston assembly will move to the left. If I keep the pressure static in there and I increase the pressure in there, the whole assembly moves that way. So that's the mechanical illustration of pressure energy. So what we're looking at in an injector is velocity energy or dynamic energy. And the force imparted by a mass is a half mv squared. Now, if you look at this equation, it's very simple. The dominant term is v squared. And so I just want you to think of knocking a nail into a piece of wood. If you put the nail in and put it under a press, that's the equivalent of pressure energy, which we just looked at on the previous slide. If we hit it with a hammer, with the mass of the hammer, we're actually imparting a velocity to that mass and accelerating an acceleration onto the nail, and the nail goes into the wood, does it not? So how do we relate what we had with the piston assembly to a dynamic assembly? So here we have a mass of fluid going through this nozzle, and it has a velocity through here. So m1 v1 squared is equal to m2 v2 squared. In other words, what's going that way is balanced by what goes that way. It's probably a little bit easier shown in the next slides. So here's steam, here's the cold water, and the cold water condenses in the steam. The steam has a high velocity, which we saw before. anything up to 3 times the speed of sound. And it's the V squared which is doing the work. So it's a big impulse on the cold water, accelerating it through the nozzle. By the time it comes out here, it's still traveling very fast, and it has a vena contractor and an outlet velocity. So here we have the water nozzle one way, and here we have another water nozzle the other way. If I put them together, if I balance it, so that one, the force from that one balances the force from that one, obviously what will happen in this example is water splayed around everywhere. So what we do is we bring them together. We have a bit of a nice lead in here, and we balance them. So if the velocity times the velocity squared times the mass of water going through there is greater than there, the whole shebang will feed through there. So the divergent nozzle for the delivery cone works like this. The pressure coming into it is very low, but it increases as you come through the nozzle. And conversely, the velocity is decreasing as it goes through the nozzle and comes out very low at the other end. So we've got high pressure, low velocity there. We've got low pressure, high velocity here. And it's that bumps up the clack valve and enters the boiler. Now, the injector that Giffard developed had a solid combining cone. And the great difficulty was how to get it started, because you had to persuade the steam to mix with the water. If you overdid it, it wouldn't condense in the water, it would shoot the water back from whence it came. So you noticed at the top end of the Giffard injector, all that gubbins was there to control the steam pressure and the volume of steam that comes through here to start it up. Once you've started it up and you've established the jet, then you can open the steam valve and off she goes and she's feeding. So to try and overcome that for locomotives, you can imagine the locomotive going over rail joints, going clickety clack, and the first major clack you come to, the injector knocks off and it won't start. You have a high pressure steam coming out the overflow and frightening everybody to death. So we split the cone and we have something like this in essence. So steam comes in there, air gets blown out and goes down to atmosphere through the overflow, and this is how it works. So here is our water feed. It's an airtight feed. Absolutely important to have it airtight. No leaking glands or anything, because they won't work. And we have another box round there and a valve. And what happens is you emit the steam. And even before you emit the steam, you can open the water feed and the water will flow through here and out to atmosphere through the overflow pipe. And you get air, steam, and water in the overflow. So here it's picked up. We've got steam coming through here, water up here. It's mixed in the water. It's coming out a high velocity jet at the end of here, and it's being transformed back into pressure energy at that end. In here is a high vacuum. And you'll see later on when we talk about hot water injectors, how necessary that vacuum is. Also, if you've got a steel boiler, do not use an injector that doesn't have a check valve at this end, because you will suck in a lot of air. I can assure you, if you put your finger over the end of these little miniature injectors, it'll try and suck your finger up it. So air in a boiler is death. So it's oxygen. Oxygen supports corrosion. So next one. Miniature injectors, in fact, any injectors, ordinary injectors, work best between 40 and 70 Fahrenheit. They will work up to 100, but the feed delivered will be reduced. As the feed temperature rises, its ability to condense the steam is reduced. Quite obviously, steam won't condense in hot water. Also, the vacuum in the combining cones decreases, and that causes boil off. So the thing just squirts steam out of the overflow and it won't work. So when you've got this thing up and running, what you want, at least from the output, is the output pressure to equal the boiler pressure. So here at 100 pounds per square inch, it must be at least 100 pounds per square inch on this line to enter the boiler through the clack valve and feed it. If you throttle the output and put a pressure gauge on it, you'll get a curve something like this. And you can see that it's practically all the way up here. This is simplified, of course. It's double the pressure that's going into the boiler. So there's a big reserve of pressure here. It gets to a point where it struggles and it can't do any more. And it comes down this line here, and the output pressure and stall pressure, as I call it, meet at this point here, sudden death. That's it. Can't get any more out of it. The injector won't feed anymore. If you want more out of it, you've got to have a different design of injector. It's important to realise this. So basically, this area here is your reserve. Once you've run out of reserve, there's nothing left. So when you test the boiler, an injector, I always do it this way with, if I issue a certificate, I just make it simple like this. So at naught, there's nothing, is there? So at some pressure, it will pick up and feed. Most of these miniature injectors will pick up between 20 and 30 pounds per square inch and start feeding, but not a lot. At the working pressure, typically 100 pounds per square inch, there is always the safety valves lifting, and if the safety valves lift but they don't quite clear all the pressure, you are allowed a 10% margin, and the injector must be able to pick up within that 10% margin. So if you're working at 100, it has to have a performance that will pick up at 110. At some point, there is a dry feed point. I usually rate them at 80 pounds per square inch. So if it's a 20 fluid ounce injector, it will deliver 20 fluid ounces of water at 80 pounds per square inch. Below the dry feed point pressure, the steam has a lower velocity and a lower energy level. Therefore, it can't entrain so much water and it can't feed so much water. So you'll see people knocking back the water feed up to this dry point just to get the injector to run dry at the overflow. Above that, you can open the feed water full bore and it will feed up to its drop dead point. And that's how I show what this injector will do. So let's look at the whole thing. This is a very, very simple boiler. And we have a check valve here feeding water into the boiler. We have a water circuit from the discharge of the injector after the delivery cone through a check valve there and up through another check valve there. On a locomotive, there could be anything for 20 to 30 feet of pipe up to the clack valve. So that's full of water. If it isn't full of water, it's full of air. And if you put the injector on, all that air is going to go into the boiler and play absolute plagues with your corrosion. So apart from having to fill it up with water every time, so that's why you always put 2 check valves on it. From the water tank, as we said, ideally about 70 degrees Fahrenheit, there's a primary filter. There's also a secondary filter somewhere here and a water valve. Steam from the boiler is taken off through a steam valve and pushed in through the steam cone. Let's have a look at some full-size injectors. This one takes steam from the boiler through here and into this chamber. And on the Giffard injector, he had lots of screws to try and regulate the steam going in. So on this one, as you open the handle here, it not only opens this valve here and allows steam to go through this nozzle, it also limits the amount of water that can come in through this plug here. So when you're just starting, it limits the water. As I said to you, at low pressures, the water delivery will be less. And as you open this valve, eventually that back collar hits that collar there and pulls this right out and allows more water to feed through the combining cones. It has the sliding ring that slides up to that face there. When there's vacuum in there, it pulls that up onto that ring. If you don't get a vacuum in there, you haven't got an injector that will work. And it goes through all these holes here, and it eventually goes through the delivery cone into the boiler. And there's this check valve here that stops the air coming through this. It's an annular space between here and there, so that communicates with that. When it's starting up, the steam and water bumps up that check valve and comes out here. Once it's going, there's a big vacuum in here, pulls the valve down and stops the air getting into the boiler. That's one type. This is the Premier, very similar to the Pemberthy, and it's dead simple. The valve here is what allows the water to escape through that valve out into atmosphere when it starts up. As soon as the jet is established, that has a high vacuum in, pulls the valve, air pressure pushes the valve down onto the seat, and it feeds, and that valve stops air going in through here into the feed water. So steam cone, combining cones, and delivery cones. This is the Sellers USA patent. It's a brilliant injector. As far as I'm aware, all New Zealand government railways steam engines had these fitted, and I'd actually operated one in New Zealand, and I can tell you they're absolutely brilliant. They're in the cab, would you believe? So they all lift water through here. They've got a special valve that allows water to be restricted when you start, and you can regulate it on there. And if you pull the valve right open, steam comes through here, through this annular passage here, and also through the main nozzle. And it's very powerful. And at some time, you can open the water up, and the water will flow into here and will be entrained furthermore in through here and through here. And they are absolutely brilliant injectors. And that's the check valve to stop the air going in. This is the most usual one that British Railways fitted. It's the Davis and Metcalfe one. And you can see it's also got space for taking supplementary water in. The water comes through here. And this is a non-lifting one. So steam comes through this annular space here. If you're clever with the steam valve, you just crack it open and it will tend to go through here and entrain the water. Once it's starting to pick up, open the steam valve fully and away it goes and delivers up through here, and the overflow goes out through there. The clever thing is about these is the fact that all the parts are exchangeable, and if you tend to get wear on this here and this here, and all you do is take it to pieces, take one out, put a new one in, and you're back in service. So it was designed specifically for loco shed operations where maintenance is a big issue. This is my favourite. This is the Swindon one. And Wiltshire wisdom works very well here, and I think they take the biscuit for this one. Ever so simple. This plate here is very cleverly made. It pivots about there, and the whole of this can pivot about there and open up. That stop comes up on there. And once you put the steam on, that will lift. It will take all the air out and drain the water. And once the vacuum's established, air pressure pushes this down and you're away and feeding past the check valve there. And this little valve here stops the air going in through the overflow. It's very light spring on it. So when it's starting up, it pushes it off the seat. And once it's going, it stops the air going into the boiler. So that one I call the mother-in-law injector for the obvious reasons. And there's one, well, two in fact, fitted onto a class 4 up in Lancashire. Quite a big chunk. I did mention about hot water injectors. I've never seen one actually in my career. I did try and make one, but it wasn't very effective. I got up to about 110 feed water temperature, but its delivery wasn't particularly clever. This one, it works by lifting up this delivery cone, and it's a lap fit inside there. And the idea is that these valves are very close to the gaps. And the reason is to get as high a vacuum as you can to stop the water boiling off. And apparently these did work, but I've never seen one and I've never experienced them. So I thought I'd put it in just to give you an idea that theoretically, at least, and practically here maybe, they do work. As a practical engineer, I would point out that in the water, you've got a lot of dissolved salts, and you've got solid particles, and they do tend to wear. You imagine, it's like a sandblaster gun. So anything in the water that's solid will wear these like fury. And can you imagine a lap fit in there? Any dirt or slime or anything that gets in there is going to render that almost impossible to move. So how good it was, got my doubts. Give you some idea of what the Davis and Metcalfe would deliver. So this is 5 gallons a minute, and you can see 1.25 inch pipes, and you go up to the biggest one, number 13, and you're up to some big pipe work there. Exhaust steam injectors. Now, basically, these are a means of feed water heating. The big problem for marine installations is the presence of oil in the exhaust. And I think all of you that have got working steamboats will know that you have to have some clever bits of wadding somewhere to get that oil out. Because once you get oil in the boiler, it breaks down and forms acids, so you don't want that. An oil trap only partially removes the oil. So I'll just put these in for the sake of interest. This is a Class H exhaust injector. You can see here the exhaust steam comes through here, and these valves are automatically open at this stage in the proceedings by virtue of this steam cylinder here. And once it's going, this area here fills up with steam, and miraculously it comes out the other end and goes into the boiler. What it does, the exhaust steam heats the feed water. So it's effectively a high temperature injector. You can see the gubbins is controlled by this steam valve here, combined steam and water valve. There's a clack up there that allows the delivery to go into the boiler, and that wheel valve opens and applies steam through there and gets it started. Here's the oil trap. You can see there's a helical deflector there, and the idea is you get the oil into this ball-shaped area. There's a drip valve in it, and if you're lucky, not too much oil goes over into the feed water through here, and it's the steam for it is taken off the blast pipe. So this stage here is the engine running, the injector not working. See, the exhaust steam valve is shut, that's vented of steam, and the water is in the thing but not doing anything. So the next case is when the engine's running and the injector's working with exhaust steam, and the valves are open. It doesn't work only on exhaust steam, it has to be supplemented by live steam. So there's this converging nozzle here, which somehow gets it to feed. And the next one is engine standing or running, no exhaust, and you've got live steam coming through here. And this chamber also fills with live steam, and somehow or other it gets into the boiler. The actual working of it, I don't fully understand. You control the water rate with this eccentric peg on here. So you turn this handle around, vertical handle there, and it pulls the cone backwards and forwards. How they ever worked long periods of time, I don't know, but apparently they did. Testing injectors. This is how I test an injector. I made this special valve here, which takes the delivery from the injector and pushes it through what in electrical terms is a diode. So it can't come back, it can only go forward, and it's counter pressured by steam from there, and it can overflow there. So when it's running normally, this pressure gauge here reads the delivery pressure, which should be the same as the boiler pressure. And it delivers water through there, and you can measure it in a measuring cylinder or whatever. So just to explain the valve a bit more, the area between there and there is exactly the same as there and there. So the pressure on this end equals the pressure on that end, and that gauge reads it off. There's a gland in there, of course, when you close that, that screws this hard up against that and stops the flow into the atmosphere, and you pressurize the delivery, and you'll see that gauge go right the way round. And that is the margin, the reserve that I told you about, very often twice the delivery pressure. And you can get that curve that I showed you drawn from taking this through various pressures up, maybe 20 pounds per square inch at a time, and you'll develop the curve and you'll see what the injector is capable of doing. These are some injectors I made for a guy in America. They have got a non-return valve on, so they're for use on a steel boiler. This is one I made for a traction engine, 3 pints a minute. And this is my test rig. And I made some quite big injectors for traction engines at one time, but they were uneconomic for me to make with a centre lathe. You really need all the CNC to do it properly and make a profit out of it, so I packed in doing them. But there's this special valve you can see, and you can measure the output pressure, you can measure the boiler pressure, and you need a clock to time how long it's going so that you can work out the flow rate. And it was gas fired, very simple. Steamboats. Well, you have to have cold feet water. So it would be manual operation only. I don't think you could automate them, which you wouldn't like in a steamboat probably. Not suitable for feeding closed or open loop condensing installations from the hot well, because obviously it's hot water. And not suitable for water tube boilers, because if you do entrap any air, it's not going to do them any good. Suitable for feeding tank type boilers, however. So if you've got a loco boiler or a vertical boiler where there's it's non-condensing, it's ideal. Or if you've got a condensing system and the amount of water in the system is going down and you can't replace it by pumping, you put the injector on and it supplements the boiler feed. That's probably probably it. So if you've got any questions, fire away.
Thanks, Bob. Right, anybody got any questions? Oh, it's interesting you mention of Davis and Metcalfe, Bob. I was, I think last year or the year before, I was in Romiley where their factory used to be, and it's a
Injector
series of,
works.
yeah, it's a series of flats now. I remember going there once on railway business, and it was a real old school factory where you washed your hands in the workshop. They had cast iron signs reminding you to to turn the tap off after you'd washed your hands.
Yeah, happy days.
Mm,
Well, this isn't a question, but a comment. I found it very hard to see the end of your pointing, your pointing stick, whatever you call it.
Oh, yes, this little fella.
Yeah, it's very small.
Yeah, I don't know how to make it bigger.
Well,
There must be a way you can do it in the, but I haven't worked out. I've got Windows 11 now, and I find it very hard to use. But it's like everything new. Eventually, you get used to it, but I haven't cracked it yet.
right.
Sorry about that.
No, well, I apologize for appearing critical for us for a
Oh,
fascinating
that's all right. It
file.
did occur to me actually to try and do that. I did feel it was a bit small, but no, that's fine. There's no offense taken on that at all.
I do have one question, Bob.
Yep.
How many pounds of steam to deliver a pound of water, generically speaking?
Oh, about it's about 10%. So if you're delivering 30 pounds of steam, 3 pounds of it is water, 3 pounds of it is condensed steam. Something like that.
More efficient than pumps, then? Do we think?
I would say so, yes. There's no moving parts to wear except the valves. They're always, well, most locomotives use them. I gave up pumps years ago. You do use pumps when you've got a feed heater on them. So the Daybeg system used to use pumped water, or if you want to pump hot water, you need displacement pumps. But for cold water, I mean the highest pressure one I'm aware of was number 10,000, the LNER engine, which worked at 400 pounds per square inch. Was it something like that? I'm not quite sure now.
I'm not that.
It was a water tube boiler.
Yeah, the hush hush. Are we talking
Hush
about?
hush. Yes,
Yeah,
that's right.
yeah.
And the story goes that at Doncaster Works, the guy who did the injectors mixed up the parts from the special one that Davis and Metcalfe developed for this engine, and they all got Davis and Metcalfe got slated because it wouldn't work. But eventually they got it to work, I understand.
Thank you.
If I could jump in here and thank Bob for what was a very useful and informative presentation. Those of you that know I'm down in New Zealand, I thought you might like to know that I thought it's significant enough to get up early this morning. It's Wednesday here, and I'm now off to explore the Burt Munro Motorcycle Museum. And I'll see you, those of you who are committee members, back in the UK next weekend or the weekend after that. Thank you very much again, Bob.
You're welcome, Kevin. I did enjoy my stay in New Zealand. Absolutely fantastic.
Yeah, we're enjoying it here now, and unfortunately we're nearly at the end of our trip, so Gilly's giving me a hard time to go out and do some sightseeing. Thanks again. Bye for now.
Good on you.
Fire away, Michael.
Yeah, I have a question. Does anybody in this group know anything about Derek Brown? He wrote a book about making small injectors like this one. And But I was trying to, I had some questions for him, and as near as I can figure, he either died or he's at a home or something.
Yeah, I know Derek Brown very well. He's a member of the Society of Modern and Experimental Engineers, as I am. And I did do some testing for Derek when he was writing his book. I don't necessarily agree with all the things he's put in his book, but he's a lovely guy. I understand he's not been that well in recent times. But yes, it's basically all there. I think my book actually gives you a bit more about the overall working of them rather than how to make them. But I haven't sold many copies of my book because it didn't work out the way I wanted it to. But there you are.
Yeah, I mean, this one worked pretty well. This is the largest one in Derek's book, and it will put out about 34 ounces per minute, and it doesn't cut off. And with 100 pounds in, it will actually continue pumping a little bit up to about 160 pounds.
Yeah, if you want injectors to work at higher pressures, you have to change the design of the combining cones, basically. The steam is at higher energy levels, and it takes, what goes through it is going in microseconds, but you have to have a longer cone for the steam to condense and mix with the water and make the jet at the end of it. So that's basically what you have to do to increase the pressure. The highest pressure one I made was for a traction engine, which was, and I made several of these, working at 200 pounds per square inch. And obviously it had to go up to 220. And yeah, it's all possible to do. The most ticklish thing to do with the small ones is to get the vacuum in the combining tube. If you get any leakage there, the performance goes right off, or any air that gets into it. That doesn't help them either.
Just to, it's Richard, just to validate what you were saying about temperature of feed water. We had a Ransom's agricultural traction engine for many years, which had an engine-driven pump, on the side of the boiler, and the water circulated round when we weren't using it into the boiler. So therefore, it gradually got heated up. So therefore, consequently, the water temperature in the tank gradually rose. And so therefore, the injector worked fine when it was cold. But once you got the you'd been running for a few hours, you'd had it. The injector wouldn't work, wouldn't pick up.
Well, it wouldn't. And people with traction engines use water lifters. And what propels the water lifters? Steam.
Yes.
So you get hot water in the well tank, and the injector says, "Oh no, I don't like that."
No, I don't know. How do you get on with your roller, Brian? Is yours?
I've just the same problem. I think in the summer I had some on hot days and using the water lifter.
Yeah.
You can get into a period when it won't feed very happily.
No.
I guess the other question I was going to ask Bob is obviously sometimes injectors can be temperamental, and often I find that cleaning the cones or cleaning the whole assembly and cones in citric acid tends to get them going again. But what are the key points in terms of wear or what are the things to look at or the areas to focus on in once you've got past the possibilities of the clack leaking or the steam valve leaking or hot water, things that would cause the injector to be hot?
Well, I did have, when I put this talk together, I had a lot more slides in. I decided to take them out because I thought it was too much. You reach saturation point and it would have been too much. But basically, the most important cone in the injector is the steam cone, because if that wears, either at the tip or at the throat, then it doesn't take many thous to increase the area because it goes up in the square, and you then put too much through and it doesn't balance the water. And so because it doesn't balance, it lifts the air valve and comes out the overflow. So you do get sediment in water, and that's why I put the filters in to try and get the sediment out. The flow rate isn't that fast, so you know an open cell filter will handle all the water you want, but it does need to be cleaned, and obviously you don't want sediment and dirt getting into the boiler either. So basically you're doing the right thing with the citric acid. Get them nice and clean, and use on the little tiny injectors I use dental brushes, you know, between your teeth. Use them in the cones if there's anything in it that won't shift with the citric acid. But a lot of these cones that enter the steam cone entering into the combining cone, they get very thin on the end, and eventually they wear away, or they end up serrated, and that plays havoc with the jet that comes out, the steam jet. Like I said right at the beginning, you're aiming for a parallel jet out of the steam cone, and if that deflects, it's trying to push the water out rather than entrain it and condense in it and impart its energy to it.
Oh, thank you. Right. Are there any more questions?
It's made me think about two things. One is superheated steam, whether it's actually better having that or not, the injector feed.
I can't really answer your question because I've never come across a superheated steam injector, and I don't really know whether you'd get any improvement on it or not. The velocity would certainly be higher. You get a bigger kick out of it. I honestly don't know.
Well, it never crossed my mind.
I regret I can't answer your question, but it is a question that's gone through my mind before. You know, what would happen if you put superheated steam through it? Interesting one, that. But you don't need it, so if it ain't broke, don't fix it.
Yeah, and the other thing is, there was in Funnel magazine a good few years back now. Bill Hall did it was just a 2-page thing on how to make a bilge ejector, and it was all quite detailed. And I thought, all I need to do is make an injector that doesn't work.
Yeah,
everyone's got one of those. So
it's dead easy.
I made one, and it's dead easy, and it works perfectly.
Yeah, they're a real boon to a steamboat owner. The only thing is, don't let the water authorities see you putting anything over the wall. They won't like it. Actually, with a bilge ejector, you can discharge it into a tank. You know, if you got an oily bilge, which hopefully you haven't, but if you have, it just squirt it into a tank. Don't put it over the side. When I was at sea, the first ship I went on, being a raw engineer apprentice, my job was to pump bilges and trim the ship. And my goodness me, in those days we used to put all sorts of rubbish over the side. And when I got a bit further along my career, the edict came from whichever pollution society was dominant at the time: thou shalt not pump anything over the wall. So we had to put it in settling tanks, and there was a hell of a lot of it. So you actually had to pump it out when you got into a port. So quite a big problem disposing of bilge water, or dirty bilge water anyway. Salt water and fresh water is not a problem. And of course, tankers, I've never been on a tanker, but you know, you've got the problem of cleaning out tanks, and that must be a hell of a problem for them. I did go on the Vic 32 up in Scotland, which is a vertical boilered pickling ship. Lovely ship. It had a brand new boiler in it. And, you know, on the trip my wife and I went on, you could go and fire it. And Sally had a go with a shovel, and she did quite well. She couldn't get the back of the box, but I managed to. And you had a pump on board. It ever so old-fashioned, this pump. Donk, 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 donk. Took ages to feed the boiler. So I said to the engineer, I said, why don't you fit an injector to it? Oh, they don't work. I said, I tell you what, I'll sell you one. Anyway, they never did put one on, but an application like that takes nice soft loch water, which isn't hard, through an injector into the boiler, ideal feed. It did have a closed loop circuit. It did have a condenser and a hot well, but it was very open. You know, it wasn't very sophisticated. Nice boat.
You mentioned earlier that the injectors aren't suitable for water tube boilers.
No, you don't really. It's not a practical thing for a water tube boiler, because a water tube boiler, you're going to have a closed loop system on it, and you want very pure water in it. And as soon as you get any scale forming salts in the water in a water tube boiler, you're going to be in dead trouble. You get a hot spot and the thing will get red hot, and with the pressure in it, it'll burst. So you need pure water, so you have to keep an eye on your water treatment and you know, getting oil out of it. I much prefer the easy man's way of using a tank boiler or a loco boiler or a vertical boiler. Water tube boilers come with a whole host of problems, I imagine. I've not had any practical experience in the sort of size boilers you use on boats, but I'm sure if you take all the precautions, there must be loads that are in the magazines and the association. Don't see why it shouldn't work perfectly, but not with an injector.
Hi Bob. Would you have any tips on making injectors?
Tips on making them? Well, the most important thing if you make an injector is to get the cones absolutely spot on in line. If you push things together and in reamed holes, and you make the cones very carefully so that they're spot on concentric, you shouldn't get any trouble. It's when you start screwing things together, if the screws don't end up on some sort of register somewhere at the end of its screwed length, it could tilt or it could be eccentric, in which case you haven't got a hope in hell of it working properly. Most of the water will come out the overflow. Making them, well, I've made, like I say, probably about 200 of them. You have to be very, very meticulous. The design really is the key to it. If the design's clever and supports having the cones absolutely dead in line, you shouldn't have too much trouble. Don't know whether I've answered your question satisfactorily, Chris.
Oh yeah, I just wondered if you had any thoughts. I've made lots of bits and things, boilers and engines, but I've never got around to doing injectors, and I do want to have a go at it sometime.
Yeah, they're not difficult to make. Like I say, providing the design is good, then you shouldn't have too much trouble.
Okay, in terms of the angles of the cones, is that critical?
Like I said, the one that I found is most critical is the combining cone, and I found 9 degrees by trial and error was about the best compromise. There was a guy in South Africa who unfortunately is no longer with us, who came up with a profiled combining cone, and he claimed that that was absolutely the bee's knees. Well, I have tried using them, and yes, they're pretty good, but the 9 degree taper in the combining cone, I found by experience is about right. 6 degrees for the delivery, which is not that critical, and the outlet from the steam cone about 13 degrees, again not that critical.
Okay, thank you.
Right. I think if there's no more questions, then I guess we raise me to thank you, Bob. It's an interesting topic, and to go through the principles and have a concept of how they influence what are the critical parts of an injector is very useful. Thank you. And you can clap in the usual way. I think there's a symbol for clapping on the on Zoom somewhere. Thank you very much.
I'd just like to add my thanks, Bob, for an interesting talk, and to you, Trevor, for organising it for us.
Yeah.
Right. The other thing I was going to ask is if anybody has topics which they'd care to share with us on the Zoom. I'm always looking for material for these talks. I'm hoping we can have a few next year, so be very welcome if you drop me an email. Anyway, at that, I'll thank everybody for joining, and good night.
Thank you very much.
Thank you.
Good night, all.
Good night.
Thanks.
Thank you.
Thank you very much. Very interesting. Thank you. Good night.
Right.